In this video, we will be talking about some of the experimental phenomena that was observed in the late 1800s, early 1900s that led ultimately to the development of quantum mechanics and gave some experimental evidence for the belief that light also behaves as a particle. When light is shown on a metal surface, electrons are produced from the surface. This is regardless of the type of metal surface that is used. So what you have is some light strikes a surface and then electrons come off. In this particular setup, you have a cathode that has a positive charge which draws the electrons towards it, and you detect the number of electrons that are striking the cathode and with what force using a current meter. The electrons that are emitted from the metal surface are called photoelectrons. They are electrons, but because they were emitted from light hitting the surface, they're specified as being photoelectrons. This phenomena of the electrons striking a metal surface and that metal surface ejecting electrons is known as the photoelectric effect. According to classical physics, the explanation for the photoelectric effect is that light behaving as a wave has energy, and that energy is imparted onto the metal surface, and that light energy then gets transferred to the electrons. If sufficient energy is given, the electrons are ejected. So what classical physics would predict is that if the wavelength of light is made shorter or the light intensity is made brighter, more electrons should be ejected. Because, according to classical physics, the energy of the wave is directly proportional to the amplitude and the frequency. So if you have a dim light that has a high frequency, you should see a lag in time before the electrons are emitted in order to give the electrons time to absorb enough energy. Essentially, once the electrons get enough energy, they should come off of the surface. So if you shine either dim light, something that has a low amplitude, then the electrons have to build up the energy to be ejected. Or if you have light waves that have a very long wavelength, i.e. a low frequency, there should also be a ramp up time in order for the electron to absorb enough energy to be emitted. What is actually seen experimentally is that there is a minimum frequency that is needed before electrons will be emitted regardless of the intensity. That particular frequency is called the threshold frequency. Below that frequency, regardless of the intensity of light, no electrons will be emitted. As soon as you get a frequency that is above the threshold frequency, electrons start to be emitted, regardless of the intensity. If the intensity of light is low, the electrons are still ejected, but they are done so at a lower rate, less electrons per unit time. When the intensity is high, a larger quantity of electrons per unit time are emitted. What also differs from what is predicted by classical physics is that there is no lag time between when the light strikes the surface and when the electrons are emitted. So if you have a low intensity, as soon as the light strikes the surface, electrons are being emitted. And if you have a low frequency of light, no matter how long you're shining light on it, at that lower frequency, the frequency that is lower than the threshold frequency, if you're over here in terms of the frequency of light, no matter how intense you shine the light and for how long you shine the light, no electrons are being emitted. It was actually Albert Einstein, the German physicist, who came up with the explanation for the photoelectric effect. And it was this explanation that won him the 1921 Nobel Prize. Einstein's explanation also was the seed for the development of modern quantum theory. Einstein proposed that light energy was delivered to the atom in packets that he called quanta, and we now refer to as photons. The energy of a photon of light is directly proportional to its frequency, and we can use the experimental formula E, or the energy of a photon, is equal to h, which is Planck's constant, which for our purpose will be 6.626 times 10 to the negative 34th joule seconds per photon. We could also write this in terms of wavelength because, again, wavelength and frequency are inversely proportional to each other. So we can write out the energy of a photon in terms of wavelength and use this particular equation here. Energy is equal to Planck's constant times the speed of light divided by the wavelength. Again, it is the speed of light that is the converting factor between our frequency and our wavelength. The symbol for Planck's constant will be an h, and it is a proportionality constant. Again, remember that the speed of light that we will be using is 2.998 times 10 to the 8th meters per second. Let's now look at a couple of problems relating frequency and energy as well as number of photons. So our first problem is how much energy does a photon of light with a frequency of 2.43 times 10 to the 12th power hertz have? Again, remember that hertz is our unit for frequency, which is equivalent to 1/seconds. So we can use our equation. E is equal to Planck's constant times our frequency, and just plug in our values. So our energy of a photon is equal to Planck's constant 6.626 times 10 to the negative 34 joules times seconds. Now the per photon is sometimes left out. So sometimes you will see Planck's constant just written joules per second. But when we're trying to calculate the energy for light, we should add this per photon at the bottom so that we can keep track of it. Multiply this by our frequency, 2.43 times 10 to the 12th, and I'm going to convert hertz directly into the base unit of 1/seconds. So again, this unit here is the hertz, just converted into the base unit of 1/seconds. So what we can see is that our seconds cancel out, and this will give us units of joules per photon, which is essentially what we're trying to find. How much energy does a photon of light have? So if we figure out the energy per photon, we will have our answer. So plugging this into the calculator, you'll get 1.610118 times 10 to the negative 21st joules per photon. In terms of significant figures, our first value has 4, our second value has 3, and so our end answer will have 3 significant figures. So our answer would be 1.61 times 10 to the negative 21st joules. Because of how the question is asked, how much energy does a photon of light have, we would take our number here and multiply it by 1 photon, and so we would have an end value of this much here. This is the amount of energy in that 1 photon. If we left the per photon, that wouldn't quite be accurate. It would be the same number, but the units for this, because we're asking for the energy of an individual photon, we wouldn't have the per photon there. Okay, looking at our second question, a nitrogen gas laser pulse with a wavelength of 337 nanometers contains 3.83 millijoules of energy. How many photons does it contain? Okay, so we have the total energy of the particular energy pulse of the laser, and we know the wavelength of the light. So what we can do is our game plan will be first figure out how much energy each individual photon has, and then take the total energy, divide that by the energy per photon, and that should give us the total number of photons. So instead of using the equation we did before, we're now going to work with one for wavelength. So our energy is equal, well, we can start with our previous equation. We have the frequency here. We instead want wavelength. we can go back to our equation relating wavelength and frequency. The speed of light is equal to the wavelength times the frequency. What we are ultimately trying to do is replace in our equation this frequency here with wavelength. So we need to come up with a way of writing out our equation in terms of frequency. So we divide both sides by wavelength, and we get our frequency is equal to c over lambda. We can then plug this part here, our equation for our frequency, in for our frequency over here, which would give us an equation of energy is equal to hc over lambda. We can now plug in our numbers. The energy of a photon is equal to Planck's constant 6.626 times 10 to the negative 34 joule seconds per photon. Multiply this by the speed of light, 2.998 times 10 to the 8th meters per second. Our seconds are going to cancel out. Then we can multiply this by 1 over our wavelength. So that's 337 nanometers. The meters and the nanometers won't quite cancel out. We need to do a unit conversion. So that would be 1 nanometer is 10 to the negative 9th meters. Our meters cancel out, our nanometers cancel out. So if we plug this into the calculator, we will get the energy of a photon is equal to 5.89456398 times 10 to the minus 19th joules per each photon. Okay, in terms of significant figures, our value, Planck's constant, has 4, the speed of light has 4, and our wavelength has 3. So our end answer will have 3 significant figures. But because we're going to be using it in a future calculation, we're not going to cut and round just yet. We need to keep at least 2 to 3 additional digits to prevent a rounding error. So to figure out the number of photons, we can take the total energy and divide it by the energy per photon, and that will tell us how many photons we have. So this would be energy total divided by energy per photon, and that will tell us how many photons. So we have 3.83 millijoules of energy times 1 over our energy per photon, which is the same thing as dividing. So that's 1 photon per 5.89456 times 10 to the minus 19th joules. Now our joules and millijoules don't quite cancel out. We need to do a conversion. And so we're going to convert our joules into millijoules, or you could think of it as converting your millijoules into joules. 1 millijoule is 10 to the negative 3rd joules. So plugging this all into the calculator, you'll get the number of photons as equaling 6.49749 times 10 to the 15th. And just to confirm our units, the millijoules cancel out, the joules cancel out, leaving you with just the photons. Okay, in terms of significant figures, our values, this one has 3, This one here from before had 3, and so our end answer will have 3. So our end answer would be 6.50 times 10 to the 15th photons. Where the idea of quanta, or photons, of light succeed in explaining the photoelectric effect and where waves do not is that particular threshold frequency. Using light as a photon, or light as individual packets, one photon at the threshold frequency gives the electron just enough energy for it to escape the atom. That value would be called the binding energy. If the photon doesn't have sufficient energy, then no matter how many photons bombard the atom, no electrons are going to be emitted. However, even if the intensity is low, you still have individual photons coming in, and if you have a low intensity but a frequency that is above the threshold frequency, then those individual photons are coming in, striking the surface, and imparting enough energy to kick the electron off. So when you're irradiating with a shorter wavelength photon, the energy absorbs more energy than is necessary to escape. What is also observed in the photoelectric effect is that if you give more energy than is needed, you don't see additional electrons coming off. What you see is that the electrons are coming off with greater kinetic energy. That extra energy becomes kinetic energy of the ejected electrons. So what they noticed is that the kinetic energy of the electrons coming off is equal to the energy of the photon that was being absorbed by the surface minus the binding energy. The binding energy is the energy that corresponds to the energy of a photon at the threshold frequency. So any energy beyond that binding energy from the photon that is being shown on the surface is converted into kinetic energy. So this H nu here is the energy of the photon. This here is the binding energy. So to finish, let's look at a conceptual question relating back to the photoelectric effect. A metal will eject electrons from its surface when struck by yellow light. What will happen if the surface is struck by ultraviolet light? No electrons will be ejected, and they will have the same kinetic energy as those ejected by yellow light. Electrons will be ejected and they will have greater kinetic energy than those ejected by yellow light. Or electrons will be ejected and they will have lower kinetic energy than those ejected by yellow light. Pause the video, select your answer, and when you're ready, hit play again to see the answer. So if a particular amount of energy is required, i.e. the amount of energy from yellow light, ultraviolet light has more energy. That extra energy will be dumped into kinetic energy. So the correct answer will be C. Electrons will be ejected and they will have greater kinetic energy than those ejected by yellow light.